Okay guys, lecture 3. This is going to be a super important lecture for understanding what a limit actually means. Okay, look at the definition, the title of the lecture. It says, Lecture 3, the definition of a limit. The first two lectures, I was showing you the idea of a limit so that you could have the idea in your head when I give you the actual definition of a limit. And that's what's today, okay? And this is going to be fairly abstract, and that's the way calculus is, okay? So, what does it mean let's say this, what does it really mean to say the limit of f of x as x approaches a equals L, let's say. We'll use L for limit. Okay, what does that really mean? That's what we want to answer. Okay? So, let's try to take this one step at a time. Let's start with the idea that you got from the first two lectures. Okay? The idea is that y, or f of x, whichever you want to say. Okay, remember, always remember that x is the x value, f of x is the y value. Okay, let's just write f of x instead of writing y. Okay, it means that f of x approaches L as x approaches a. That's the idea that you got from the first two lectures, right? Okay. What's another way we can say that? I would like to just refine that definition down until we get a very, very exact definition. Okay, so f of x approaches L as x approaches a. What's another way of saying that? How about if we say if x is near a, then f of x is near L. Okay, good. That's getting better. Getting a little bit more specific. Okay. Now, what does it mean to say near? What would that be? Near might mean very close to, but that's a matter of opinion. I mean, for some people, 100 feet away from something would be considered near. For other people, you would have to be an inch away to be considered near. Okay? But what do those both have in common? They're both distances, right? So how about if I try to refine that sentence this way? If x is within a certain distance from a, comma, then f of x is within a certain distance from L. Okay. All right, now we're getting there, getting better. So here's what we're going to do now. Let's take this phrase, a certain distance. And let's just call that distance something, okay? Let's call that the Greek letter delta. Looks like that, okay? Now there's another distance involved as well, and that's this distance right here. Let's call that the Greek letter epsilon. So I'm going to refine that sentence a little bit more, and I'm going to say, if the distance between x and a is less than delta, then the distance between f of x and L is less than epsilon. Okay, let's rewrite the sentence that way. This is the same sentence that I'm writing over and over again. This is now the 4th time. Okay? See, I wrote it like that, and then I tried to get a little bit better, and then a little bit better, and now I'm going to write it a 4th time a little bit better. Okay? If the distance from x to a, maybe it's better to say between x and a, is less than delta, comma, then the distance between f of x and L is less than epsilon. Let's take a stock of something here. What's the delta and what's the epsilon? The epsilon is how close you want f of x to be from L. That's the epsilon. That's your margin of error. Okay? We're trying to show that f of x approaches L. So you set a margin of error. That's why we use the Greek letter epsilon. It's the Greek version of E. And we use that because that's your margin of error. Okay? So you want f of x to approach L. You set a margin of error on it. And that's your epsilon. And then you ask yourself, how close does x need to get to A in order for f of x to be within our margin of error from L? Okay? And we use the Greek letter delta for that other distance because that's the Greek version of D. D for distance and epsilon for error. Okay? All right. We can now boil this down by replacing a lot of those words with symbols, and then it won't be so long. Okay? Let's do this. How do I write the distance between x and A? How do you write the distance between two things? And keep in mind now, you don't know which number is the bigger of the two and which is the smaller of the two. You just have two numbers, x and A. What one thing can I write to represent the distance between them without me knowing which one's bigger and which one's smaller? The answer is we write absolute value of x minus A. Or you could write A minus x, okay? The important thing is having the absolute values there. That's how you measure the distance between two things. Okay? How do I say is less than? Well, that's easy. You know that. We do that. And here's a silly question. How do I say delta? I say it delta. Okay? In the second half of the sentence, let's use symbols to shorten that. Here we have the distance between f of x and L. So how do I say that? I say the absolute value of f of x and L. And then how do I say is less than? I say it like that. And how do I say epsilon? I say epsilon. Okay, so now I can write that long sentence very shortly. I say if the distance between x and A is less than delta, then the distance between f of x and L will be less than epsilon. Oh, that's the exact same sentence, same words as what is right above it, but it's much, much shorter to write because I'm using some symbols in place of words. Okay, very good. Let's pause for a moment right there and let's look at a picture. Okay, suppose that I'm going to graph something, okay? Okay, so let's just say that this is f of x. I'll just draw a line. We don't need to get fancy. Let's say that's our graph of f. Okay, and let's say A is right here. As x approaches A, what does f of x approach? Wouldn't you agree that the answer is that value right there? We'll call that L. Okay? As x approaches A, f of x approaches L. Okay, we got that? So let's do this now. One second here. My computer just went blank on me. Okay, that's better. All right, now, what do we want to happen? Or rather, I should say this. What are we trying to show? We're trying to show that f of x is approaching L. That's what we're trying to show, right? So that's where we put our margin of error, is around L. All right, so I'm going to just pick a margin of error. Let's say this big. That's my margin of error. I want to make f of x be within this margin of error. Okay. So here's L right here. I allow myself a little bit of distance above and below as a margin of error, and we call that margin of error epsilon. Okay. So this value up there at the top would be L plus epsilon, and down here would be L minus epsilon. Okay. All right, now what I ask myself is, I say, listen very, very carefully, this is so important. How close does x need to get to A in order for f of x to be within that margin of error from L. Okay, well, let's look and see. If x is in this region, let me draw that arrow up here. If x is in there, then f of x will be in here. So what you do is you say, okay, how far away from L can I get? And you measure the same distance on both sides, and you call that distance delta. So here we would have A minus delta, and here we would have A plus delta. Actually, I'm going to erase that green line I just drew and also that red one. Okay? And if x is in there, if x is between A minus delta and A plus delta, then f of x will be between L minus epsilon and L plus epsilon. In other words, if the distance between x and A is less than delta, then the distance between f of x and L will be less than epsilon. That's how limits are defined. Okay? Now what did I say about that epsilon? I say that's a margin of error, right? And I say you place the margin of error on there. Okay? Now, how close do we want f of x to be getting to L if L is the limit? You want it to get as close as imaginable, right? So in other words, we want this to be able to happen no matter how small epsilon is. That's very, very important. Okay? We want this to be able to happen no matter how small epsilon is. So, I'm going to add a phrase. I'm going to look back at our sentence up here, and I'm going to add a phrase to the beginning. And I want to say that I want this to work no matter how small epsilon is. In other words, for any epsilon. Okay? So, for any epsilon. I'm going to leave a little bit of a space because I want to add something in there. Okay. If the distance between x and A is less than delta, then the distance between f of x and L will be less than epsilon. Okay? Alright, but what is epsilon? It's your margin of error, right? And it is a what? Look back up there. It is a distance, right? Distances cannot be negative, can they? And one other thing, we don't want that distance, we don't want to force it to be 0, because if your margin of error is 0, then it's not a margin of error, is it? The only way, if your margin of error is 0, then f of x would have to actually equal L, and we don't want to force that. We want to say it is approaching L. Okay, so epsilon is your margin of error. You don't want it to be 0, and it can't be negative, and so therefore epsilon must be greater than 0. That's why I left that little space there. Okay? All right, we're getting there. We got to still take several steps of refinement in order to get the sentence to be exact. But we're getting close. Okay. Let's think about the delta now. Look at that picture up here again. Okay? I want you to notice something. It says epsilon can be however big I want, right? That's what I said right here. Any epsilon greater than 0. So if you went to that picture and you made epsilon smaller, what would have to happen to delta? It would have to get smaller too, right? What if you made epsilon bigger? Then delta could get bigger. So in other words, this is important. The size of delta depends upon epsilon, doesn't it? So another way of saying that is there's a different delta that goes with each different epsilon that somebody might choose. So then let me add a phrase in there to that sentence to make that clear. Okay, so I'm going to say it this way now. For any epsilon greater than 0, I don't want to just go on to say if the distance between x and a is less than delta. I want to say this. I want to say that there is a delta that goes with each epsilon. So for any epsilon greater than 0, there is a delta, and that's also a distance too, right? So we want to say a delta greater than 0, okay? Such that if the distance between x and a is less than delta, then the distance between f of x and L is less than epsilon. Okay, so that's getting more specific. All right, I can think of 2 minor adjustments that we need to make this perfect. Do you remember that I made a really big deal a couple days ago, a couple lectures ago? I made a really big deal about the limit of f of x as x approaches a has nothing to do with f of a, right? Remember that. The limit of f of x as x approaches a has nothing to do with f of a. In other words, when you're doing the limit, you only care what happens as x approaches a. You do not care what happens when x equals a. Okay? When we need to build that into this definition of limit, we need to build in the idea that we don't care what happens when x equals a. So let me ask you a question. If x equaled a, then what would be the distance between x and a? It would be 0, right? So I want to build in the idea that I don't care what happens when x equals a. So in other words, I don't care what happens when the absolute value of x minus a is 0. So therefore, instead of saying right here, if the distance between x and a is less than delta, I want to say if the distance between x and a is less than delta, but not 0, there's an easy way to do that. Just say less than delta and greater than 0. That builds in the idea that you don't care what happens when x equals a. Okay? And it's almost perfect now, only one tiny little thing, and this is just a technicality really, is how are we even sure that there is an f of x? Remember, every function has something called a domain. And you can only calculate f of x if x is in the domain. So I need to just build that concept into this definition. Okay, and then we'll be perfect. And so here it is, our final version. For any epsilon greater than 0, there is a delta greater than 0, such that if x is in the domain of f, and the distance between x and a is greater than 0 and less than delta, then the distance between f of x and L will be less than epsilon. And there's our definition for the limit. Okay, so I'm going to actually write here, I'm going to say the limit of f of x as x approaches a equals L means that, and then we pick up with the word for, since that's not the beginning of the sentence anymore, I'll make the f lowercase. Okay, let me separate that from the others a bit because that's very important. I'm going to put a red box around there because it's so important. That's the definition of a limit. The first two lectures, I was just giving you the idea of a limit. Now you have the actual definition. Okay? And you need to go over that in your head over and over again. And you need to get that memorized. I've written it slightly different than the way it is in the textbook. And if you compare it to the textbook on page 15, you'll actually see that my definition is slightly shorter. Theirs is even more complicated, but says the exact same thing. I haven't diluted the idea at all. I've just worded it very, very slightly different in order to make it a little bit shorter than the way they wrote it. Okay? So, that's your first taste of actual calculus here. Okay? Oh, and this is usually referred to as the epsilon delta definition. You'll hear people say that all the time. You'll hear people say the epsilon delta definition of a limit. And this sentence is what they're referring to. Okay? Let's just do a couple of practice problems here. We'll do some easy ones today, and then in the next lecture we'll do some that are a little bit harder. So let's just look at a function here. Let's just say f of x equals I'm going to write a line. Okay, let's say f of x equals 1/2 x plus 1. So that would be a line with a slope of 1/2 and a y-intercept of 1. So that's going to look something like this. Okay? Do you agree that the limit of that as x approaches 4 would equal, well, let's look and see what it would be. There's 4. So as x approaches 4, that means the graph would be approaching this location right here, which has a y value of what? 3, right? So that limit is 3. Can you see that? So what if somebody comes along now and they give you a margin of error of, let's say, 1. Margin of error of 1. So you want f of x to be in this right there. Okay. 3 plus or minus 1. So that means anywhere between 2 and 4. So the question I'm asking is, how close does x need to get to 4 in order to make that happen? Well, let's see. X would have to be between 2 and 6, right? So what it, whoops, I didn't mean to erase the number 4. So what is the distance here that we can deviate from the number 4? That distance is 2, isn't it? So do you see that if the distance between x and 4 is less than 2, but I don't care what happens if x equals 4, so I'm not going to allow that distance to become 0. Then the distance between f of x and 3 will be less than 1. But if somebody changes that margin of error, remember that's how the whole thing starts, is you pick a margin of error. I picked a margin of error of 1. Okay? If somebody changes that margin of error, then our allowed deviation down here will change. Here's our epsilon. And here's our delta. Generally speaking, if epsilon got bigger, then delta would be allowed to get bigger. And if epsilon got smaller, then delta would have to get smaller. Okay? That's the idea. Based upon the time, I think we'll just leave it at that one example. Now, here's the thing we're going to do in the next lecture. It's going to be a little bit harder. In the next lecture, I'm going to say, what if somebody doesn't tell you how big their epsilon is? Can you still find the delta that you need to go with it? Okay? All right. Thank you very much for listening. Please write that definition down and say it in your head over and over again. You need to know that definition. You should memorize it. Remember that I told you on the first lecture that every single concept in calculus boils down to a limit of some sort. And that red box is the definition of a limit. So that means that every single concept in calculus depends upon that one sentence. So you must know that definition. Okay? All right, come to the Zoom discussion if you have any questions, and I'll see you there or in the next lecture.